Welcome back to Analog Electronic Circuits. This is lecture 12 and we are going to continue from where we left off in the last class. We are going to talk about multi-transistor amplifiers. Now, in the last class we saw that when you have got your standard common source amplifier, this is your standard common source amplifier. We saw what we noticed was that a lot depends on this resistor RD, right. The gain of the amplifier was minus GM times capital RD in parallel with RDS. So, if RD is small, then the gain of the amplifier drops, but then the signal swing that I have at the output, that is also dependent on RD, right. So, the if I have got a current ID over here, then the voltage over here, DC voltage over here is VDD minus IDRD, right. If the current is capital ID, then the maximum signal current, assuming a sine wave, is small is also capital ID, right, because the signal current, the total current can't go below 0, all right, total current cannot go below 0. At all times, small I sub capital D has to be greater than 0 at all times. This was the second condition for evaluating swing limits. Small I sub capital D is capital ID plus small id, which means small id always has to be more than capital minus capital ID, all right, which means that if you say that the current is a sine wave riding on top of, so the signal current is a sine wave, if you say the total current is a sine wave riding on top of capital ID, if you say that, then the least value is 0, therefore, the maximum value is 2 times ID. Okay. Maximum value is 2 times ID. What is the minimum value? Minimum value is 0. If the minimum value is 0, if it is riding on top of capital ID, then the peak value is 2 times ID, is not it? Yes? Okay. So, the peak value is 2 times ID, minimum value is 0. Automatically, that is the current coming through RD. So, when the current coming through RD is 0, the voltage over here is just VDD. When the current over here is ID, then the voltage over here is VDD minus IDRD. And when, so this is the mean. So, at this point of time you have got VDD minus IDRD as the voltage. When ID is so much, you have got a voltage of VDD at the drain, and when ID is 2 times ID, you have got a voltage at the drain of VDD minus 2 times capital IDRD. Is this okay? So, if small id is a sine wave, then the maximum amplitude of the drain voltage. So, the drain voltage is nominally VDD minus IDRD, and then it is riding on top of that. Okay. So, if you ask me to draw a waveform for the drain voltage, it is going to look like this. This peak is at VDD, the nominal value is VDD minus IDRD, and the lowest value is, the trough is at VDD minus 2 IDRD. The amplitude is just IDRD. Is it okay? Of course, I have thrown out the load, right, there is no load over here. Once you put in a load, things will change, agreed. So, the amplitude of the drain voltage is nothing but capital IDRT. Okay. So, effectively what it means is that you want RD to be large to get good gain, right, but when RD is large, other strange things happen. ID becomes small, for example, right. In this calculation we did not look at VDS at all, right. VDS also has some limits. So, this is assuming that VDS does not limit you. VDD minus 2 IDRD is assuming that VDS is not going to limit you, right. For this particular situation, VDS could have limited you. Okay. So, in any case, RD is something of great importance over here. RD needs to be large to give you good gain, and if RD is large, unfortunately VDS starts limiting you. So, you do not get good swing, although IDRD seems like it is going to be the amplitude. However, VDS is going to cut you off over here, right. So, that is not really going to be the amplitude, final amplitude. All right. So, we have this problem, right, gain is being limited effectively. What can we do? One simple thing that we can do is have two amplifiers, right, have a cascade of two amplifiers. So, this is your bias circuit, you use the same bias circuit for the other one. Right, and then couple the signals in and out. Okay. So, this is a possibility. So, now you get the benefit, you get gain of one stage is so much, gain of the second stage is so much. So, the total voltage gain is the product of the two voltage gains. Is this okay? There is some little bit of loading over here which you will have to account for. This resistor over here, these two can be made arbitrarily large. So, this should not matter. You can make these mega ohms, giga ohms, nothing is going to change. Okay. This is okay, this is a cascade of two amplifiers. Now, this is one possible strategy. What about the swing? The swing problem is just the same, right. If you can swing so much, I mean nothing changes as far as the swing is concerned. You are limited by RD, ID times RD, right. On one hand, you want ID to be small, right, R d to be large. On the other hand, swing is being limited, all right, by both I d and R d. Okay. So, this is one possibility in any case. There is a second possibility which is just like the cascade, but we call it the cascode. Okay, there is an O over there, and you will not find this word in any dictionary, right. This is not an English word, this is a word that is used only in analog electronics, it is called the cascode. And what we do over here is, remember we at one point of time had discussed these voltage sources and current sources. We said that a voltage source is a circuit which has a low output impedance, a current source is a circuit which has a high output impedance. Likewise, we said that something which is voltage controlled will have a high input impedance, something which is current controlled will have a low input impedance, right. And then we referred to the common source as possibly a voltage controlled current source, and then we referred to the common gate as possibly a current controlled current source, and then we refer to the common drain as a voltage controlled voltage source, right. So, we had these three possibilities. We did not really make a current controlled voltage source, but that is okay, you can make with a combination. Okay. Now, what do we do? One possibility is to have a common source up front followed by a common gate. Okay. So, common source is a voltage controlled current source, common gate is a current controlled current source. So, overall you will still have a voltage controlled current source. So, this is VCCS, this is CCCS. So, overall you will get a voltage controlled current source. Hopefully a better one. All right. So, this is also a multi-transistor amplifier. So, I have got my I am drawing the only the small signal picture right now, because I first need to understand what the circuit is, then I will draw the biasing and so on. So, this is the common source amplifier and this is where you place the load, but instead of the load what we are going to do is we are going to put a common gate structure over there, and the common gate structure looks like this, and then finally you have a load. Okay. So, the thought process is that if I have a common gate structure following a common source structure, then maybe I would have made a better current source, a better controlled current source. All right. So, this is going to be our next topic, the cascode amplifier. Now, this may or may not solve the earlier problem with R d. In fact, it is most probably not going to solve this problem of R d at all. Okay. But what we are going to see is that we do not really always have to worry about voltage gain. Maybe, I mean, for example, in this circuit your input is a voltage, output is a current, right, it is a voltage controlled current source, right. So, maybe we can even work in the current domain instead of the voltage domain, right. And if you are working in the current domain, maybe the swing is not going to be that much of a problem as before. Because we were working in the voltage domain, over there swing was a problem and RD was limiting us, right. If I start working in the current domain, maybe things are not going to be as difficult, right. But anyway, this will open up a possibility of that happening. Why we are also studying this is because this is an alternative that needs to be explored. It so happens that the Cascode amplifier is a very popular circuit. Okay. All right. Anyway, so this is the structure. I am going to apply input over here and the output is this current. All right, if you want the output to be a voltage, so be it, right. It is going to be this current times this resistor, that is the voltage. But right now let us worry about only about the current, worry only about the current. So, the way we work in this course is using the Norton equivalent method. And what is the Norton equivalent method? It comprises of two things, evaluating a short circuit current and evaluating an output impedance. So, let us start with the output impedance. What are you going to do? You are going to null the input voltage source and then you are going to look in from the output and see how much resistance do you find. Now, when I null this input voltage source, what happens to this MOSFET? This MOSFET has two elements inside. One is a GM times VGS, the other is RDS. There is also GMB, but both body and source are at ground for this particular MOSFET. So, for M1 GMB VBS, VBS is equal to 0. So, GMB does not matter. For the output impedance calculation, gate and source are both at 0. So, therefore, gate to source voltage is 0. Therefore, GM times VGS is also 0. So, it does not matter. So, all that this MOSFET has as far as output impedance is concerned is an RDS. RDS 1, and then you are looking in from the drain, and hopefully you have memorized the formulae that I had asked you to memorize. You did, right? Okay. So, if you look in from the drain, the gate is terminated to ground, the source is terminated to ground through a resistor RDS 1, and therefore, the output impedance is nothing but RDS 1 plus RDS of this MOSFET plus the intrinsic gain of this MOSFET times RDS 1. Okay. Remember the formula? So, when I look in from outside, I see GM of this MOSFET times RDS of this MOSFET times this resistor plus RDS of this MOSFET plus this resistor. Okay. So, intrinsic gain of this MOSFET times this resistor plus RDS of this plus this resistor. That is exactly what I did. Intrinsic gain times RDS 1, because this MOSFET is only RDS 1, there is nothing else in it, plus RDS 1 plus RDS 2. Okay. You need to memorize this formula, you have not clearly. Okay. Done. Output impedance is done. Now, what we have to do? We have to find out the short circuit current, short circuit transconductance or short circuit current, whatever you want. So, to find out the short circuit current, we are going to first ground this, then we are going to apply a input V in and see what happens. Right now, when I am applying this input V in, if you think about this MOSFET, there is GM1 inside this, which is going to respond with GM1 times V in, because VGS is V in. So, GM1 times V in, and then there is RDS1 to ground, all right, and the rest you are just looking into the source of M2. So, let us redraw. I do not like this redrawing, but you should draw this in your mind. There is GM1 times V in and there is RDS1. GMB of number 1 device does not matter, because both body and source are at ground. So, I am not going to draw that, thank you. And then above this there is a source. With the gate at ground. So, you can use the other formula to think about what is on top, right. So, as far as this structure is concerned, looking up from here, what do you see? What do you see looking up? Use your second formula, you will find that looking up you see some impedance, right. We will do the second formula. So, then you redraw, this is some impedance looking up. So, if I have GM1V in over here, this is the source of current. This current is seeing two things, on one hand it is seeing RDS1, on the other hand it sees some impedance, right. So, there is going to be a current division, a portion of this current is going to go the other way into this source, and whatever goes into the source eventually makes its way into the short circuit. Right. So, that is your answer. So, GM1 V in, and then you have to do a current division between RDS1 and what you see into the source. What is it that you see into looking into the source? So, if you think about the other formula, looking into the source, you normally see RDS of this MOSFET plus whatever was on the drain, nothing is there on the drain. So, it is just RDS2 divided by 1 plus intrinsic gain of the MOSFET. Okay, this is the impedance that you see looking into the source of M2. Okay. So, how is current going to divide? This current is going to divide into two pieces. One portion is going to go out through RDS1 and another portion is going to come through M2. What is the portion that is going to come through M2? It is proportional to the other resistor RDS1. Okay. So, this fraction of the whole thing is going to proceed into the short circuit and the whole thing is nothing but GM1 times V in. You see how I constructed the expression? I started with GM1 V in and then there is going to be a current split, right, current division. Current is going to divide proportional to RDS1, right. So, GM1 V in times RDS1 divided by RDS1 plus this impedance and this impedance is so much. So, I just wrote it down. All right, and then you go a step further and simplify. So, the Norton equivalent current is nothing but okay. And you can multiply numerator and denominator by this factor. Okay. And this is the transconductance and then the next step is to multiply this whole thing with the output impedance and that will give you V out. Should you do that? No, the output impedance and the load. Okay. So, over here we did not consider the load, right, we kept the load outside. So, let us not do this V out by V in, let us stick to what we have, right. We have the short circuit current. So, this is the transconductance, okay. The transconductance of the circuit is so much, the output impedance is so much. So, this is the complete Norton equivalent model of the circuit. All right. Now, if you want to find out the gain, then the output impedance has to be modified a little bit by the load impedance, right. I mean you can bring the load impedance inside and then find the output impedance if you want to look at the voltage gain. Okay. So, let us just quickly do that. So, it is this output impedance in parallel with the load impedance. Now, notice something, this output impedance over here happens to be RDS1 plus RDS2 plus GM2 RDS2 RDS1 plus GMB2 RDS2 RDS1. So, this output impedance is the same as this denominator, okay, just pointing it out, all right. So, if you want to write this as G out, or rather if you want to write this as R out, you have some numerator okay. I need to point out one more thing, hang on. So, this numerator and divided by R out. Fine. The output impedance happens to be this in parallel with the load. So, the total output impedance is 1 by G out plus G L. So, this quantity times G out output conductance plus load conductance. Okay, so, this is how it is going to look like, more or less. Now, I want to point out one more thing. Look at this expression. This expression is 1 plus GM2 plus GMB2 RDS2, 1 plus GM2 RDS2 plus GMB2 RDS2. Okay, times RDS1. So, if you look at this numerator, then this denominator is the same numerator by GM1 plus RDS2. Also notice that this factor is very large. RDS1, suppose the intrinsic gain of a MOSFET is 20, suppose. Okay. So, GM2 RDS2 is something like 20. Okay, it is more than 20, 100, okay, fine. So, let us say intrinsic gain is 100. So, this entire factor is of the order of 100, 1 plus 100, right, GMB2 is smaller, right. 100 times RDS1 plus RDS2, fine. And what have you got here? You have got exactly the same thing, 100 times RDS1 times GM1. So, you have got 100 times RDS1 plus RDS2, 100 times RDS1 times GM1. RDS2 is also, you know, a large number, but not as large as 100 times RDS1. So, therefore, the entire denominator is dominated by this first portion. RDS2 is nothing compared to 100 times RDS1, which means you can forget about the second term altogether, in which case these two are going to cleanly cancel out and all you are going to be left with is just GM1. What does this mean? This means that the output transconductance, the short circuit transconductance, is just GM1. What is going on over here? Are we missing something? Take a look again. How did we find out the output transconductance, the short circuit transconductance? There was a voltage V in, it got converted to a current GM1 times V in. Now, GM1 times V in saw RDS1 on this side and it saw another impedance on the other side and there was a current division. On this side it is RDS1, on the other side it is RDS2 divided by the intrinsic gain, which is very small, right. So, 100 times smaller than RDS2. So, on one side it saw RDS1, on the other side it saw an impedance 100 times smaller than RDS2. Which side is it going to pick? It is going to go through the source, right. So, all of the current, almost all of the current is going to go into the source, because current likes the lower impedance. Okay. Very small portion is going to go through RDS1, because RDS1 is much larger than whatever you see into the source, okay, 100 times larger. So, 1% current is going to go this way, 99% current is going to go that way, which means that this GM1 times V in, almost all of it is going into the short circuit. So, I applied V in, I got a current GM1 times V in going into the short circuit, which means that the transconductance is nothing but GM1. All right. You see what happened over here? You saw what happened? Going into the source of M2. So, I applied V in, it produced current. Now, this current is going to be shared, portion of it will go through RDS1, portion of it will go into the source, but RDS1 is always much larger than what you see looking into the source. So, almost all of it is going to go into the source of M2. Okay. So, whatever current it produced, all of it went into the short circuit. Fine. So, therefore, the transconductance is approximately GM1. Is it okay? Do you understand what happened over here? All right. So, this is something very important that happened. You almost sent all of the current. So, this is a current controlled, this is what happened over here. M2 is a current controlled current source. Remember, this is a common gate structure. So, whatever current went inside, it came outside, right. You applied a current, you got a certain current at the output, the same current. The input impedance of M2 is low, right, that is why it was current controlled. M1 is a voltage controlled current source, it produced a current, right, it produced a current, and that current has a nice low impedance to go through, it came out through the drain. Okay. Now, effectively what happened, the other thing that happened is that the output impedance got multiplied by a large amount. The output impedance of the entire structure became 100 times. Okay. So, it is a nice current source, because its output impedance is very large. So, at every step you are seeing over here that it is a very nice current source. It is current controlled over here, and then it is a current source, because the output impedance is very large. Overall, the circuit becomes a nice voltage controlled current source. Okay. I have applied a voltage, I got GM times the voltage as the current, and the output impedance is very high, which means it is a very nice voltage controlled current source. All right. Now, we just have to work out the gain. Let us assume that GL is very large, okay, in which case this is equal to 1. Let us just assume. Then what is the voltage gain? The voltage gain is just this other factor, which is GM1 RDS1 plus GM1 RDS1 times GM2 plus GMB2 RDS2. Okay. So, it is the intrinsic gain of transistor 1 plus the intrinsic gain of transistor 2 times the intrinsic gain of transistor 2. So, intrinsic gain of transistor 1 plus intrinsic gain of transistor 1 times intrinsic gain of transistor 2. So, this is the intrinsic gain of transistor 2. This is, so let us say each of these intrinsic gains is a factor of 100. So, 100 plus 100 times another 100, right. So, what have you got? You have got 10,000. Okay. So, this entire portion is a factor of 10,000 times G out by G out plus G L, and I already know that G out is very large. Oh no, G out is very small, I am sorry, G out is very small, R out is very large, R out is very large, G out is very small. So, it all depends on G L. So, if I make G L, for example, if I make G L 10% of G out, 0.1 of G out, then this is more or less a factor of 0.9 or something, and I end up with a voltage gain of 10,000. Okay. Any questions so far? You have got to have one question. I just did something funny. Yes. So, just like last time when we did the common source circuit, everything kind of depended on the value of R d. All of the intrinsic gain was G m times R d s, but then at the end there was a parallel with R d. Okay. So, if you think of it as an intrinsic gain kind of situation, then for the common source amplifier your intrinsic gain would have been G m 1 R d s 1, and the output impedance would be whatever your G out is, G out would be something, it is actually just R d s, G d s. Okay. So, this G d would create spoil sport, would be a spoil sport. This would spoil the entire thing. Okay. So, the same problem is cropping up over here. How are you going to make this high resistance? So, what we are going to do is we are going to take a break from the study of these multi-transistor amplifiers. We have a problem, right. Our fundamental problem is how are we going to make this large impedance R d or this large impedance, in this case R L, right. How are we going to make this and yet satisfy some reasonable swing limit and so on, right, all the other requirements of the amplifier. You have to satisfy those as well, right. How are we going to satisfy both of these requirements? Number 1, a large value over here, and number 2, some reasonable swing limits of the amplifier. Okay. So, we have this quandary, and the answer to this quandary is to avoid the use of resistors altogether, right. You can't stop using these resistors. Okay. Do not use resistors. Instead, let us try to use a MOSFET. For example, think of the following. Let us think about this. Okay. I have replaced the NMOS with PMOS devices, right. It is still a cascode kind of structure. I have replaced the input voltage with a ground, and this is in the small signal picture. Okay. This is in the small signal picture. What is going to be the input impedance of this? It is going to be, so this MOSFET is going to behave just like a resistor RDS 4. Yeah, the small signal picture of the NMOS and the small signal picture for the PMOS, terminal for terminal is exactly the same. There is no difference. Do not interchange the arrows, do not make them opposite, no, nothing, right. Terminal for terminal, it is exactly the same. So, here I have got source on the top, right. The small signal picture of this particular PMOS should look like this. Gate is at ground, drain is over here, this is the drain, and the source is at ground, right, and GM times VGS should point upwards, because that is the way it does, right. GM times VGS, it always points towards the source. Okay, this is the first time I have drawn a PMOS, all right. P channel MOSFET, it is just like the N channel MOSFET, just that the current, the absolute current direction is reversed. Okay, the DC operating point current direction is reversed. Okay, so do not worry about that. The DC current flows from top to bottom, but the small signal picture terminal for terminal is exactly the same. Okay. And what this means is that the gate is at ground, the source is at ground, therefore, this GMVGS is useless, it is not doing anything, which means between drain and source all you have is RDS. So, M4 is nothing but RDS 4. And then you are looking into the drain of M3, source of M3 is terminated by RDS 4, use the formula to find out the impedance looking in. And the impedance looking in, it is the same old formula, is nothing but RDS 4 plus RDS 3 plus intrinsic gain of M3 times RDS 4. Okay. So, here I have a situation where I can create a large impedance. Why not place this large impedance over here? Why not place that large impedance on the top side? You see what I mean? You do not have to make a resistor using a resistor. You can make a resistor using MOSFETs. What is stopping you? So, for example, over here I could have had this structure. Okay. So, this is my old thing, this is the Cascode amplifier and this is the load of the Cascode amplifier. I needed a very large resistor as the load of the Cascode amplifier, right, comparable to the output impedance of the Cascode amplifier. The output impedance of the Cascode amplifier was RDS 2 plus RDS 1 plus intrinsic gain of this MOSFET times RDS 1. The impedance of the load over here is RDS 3 plus RDS 4 plus intrinsic gain of MOSFET number 3 times RDS 4. Okay, so these are going to be comparable to each other. Why? Because the same bias current is going through, right. If lambda is similar, then RDS is going to be similar. Okay. So, now let us draw the complete circuit, right. This is understood so far. So, this is the overall, this is the small signal picture only, right, because all these are connected to ground. These should not be connected to ground, these should be connected to some reasonable voltage, right. I do not yet know what that voltage is, but maybe just maybe you could think of some resistive network which generates these voltages. You need one more resistor. Okay. You want to have a source degeneration on the bias, okay, very good. And then in the small signal picture you want it looking exactly like this. So, this has to be capacitively connected to ground, this one capacitively connected to ground, this one capacitively connected to ground, and then this source degeneration has to be shorted out in the small signal picture, and then you have to capacitively connect this to the input and you take the output correctly through a capacitor. Is this okay? This is too daunting. So, from one transistor I have suddenly jumped to 4 transistors. Okay. You will see even bigger jumps later on, but I need you to absolutely memorize formula 1 and formula 2, right. Looking into the source, what is the impedance that you see, looking into the drain, what is the impedance that you see. Those two formulae are vital if you want to proceed with this course. If you are not willing to memorize those two formulae, then drop out. Okay. It is just two formulae, right, and they are quite simple. All you have to remember is looking into the source, the impedance drops by a factor which is 1 plus the intrinsic gain of the MOSFET. Looking into the drain, the impedance multiplies by a factor, right, which is the intrinsic gain of the MOSFET. This is all that you have to remember, okay. And then accordingly you can write out the formulas, but do memorize them, and they are important, right. This entire analysis of this circuit is resting upon those two formulae, right. The output impedance of the top portion is high, the output impedance of the bottom portion is high. Then the short circuit current, the top portion is shorted out. For the short circuit current you have a short over here. So, the top portion is irrelevant, but as far as the bottom portion is concerned, that is relevant, right. You are going to look into the source and there is going to be a current division, portion is going to come out through RDS 1, portion is going to go into the source of MOSFET number 2, right. Looking into the source of MOSFET number 2, you see a low impedance, therefore, the current would love to go into that node, right, go into the source, right. So, GM1 times VGS1, GM1 times V in is the current generated in M1, that entire current, almost all of it goes into the source of the MOSFET number 2 and comes out through the short circuit. So, the transconductance is just GM1. The output impedance is large in parallel with large. The overall voltage gain is GM1, the transconductance, times the output impedance, which is large in parallel with large. So, you have a large voltage gain. So, this is the idea. So, this is a kind of setup of the cascode amplifier. I am not yet promising that this works, right. We have to really think about what this bias network looks like. I mean, maybe it is just 5 resistors like I have drawn, but it is probably likely that these 5 resistors will have to be worked on a little bit, because we have to make sure that all of these carry the same bias current, right. The value of the current has to check out, okay. Otherwise very strange things are going to happen, right. It has to have equal bias current through all of them, not, I mean, you can't have some bias current through this one and some other bias current for the next one. That is not really going to work out, right. And then at the same time you have to make sure that VDS1, the drain to source voltage of each of these devices, is enough to make sure that the devices remain in saturation at all times. So, this we have to think about a little bit. We will do that in the next class, and then we will move on to the next topic. Thank you.